Hi everyone, my name is Chen. I'm going to talk about our work, Learning Trajectories for Visual-Inertial System Calibration via Model-Based Heuristic Deep Reinforcement Learning. In recent years, visual-inertial systems are widely used in various autonomous mobile robots. Precise calibration is of great importance for VI sensors. However, it is non-trivial to collect enough measurements efficiently to infer the desired sensor parameters. So we propose a model-based heuristic RL algorithm to learn the best motion primitives and perform them on a robot arm. We model the calibration problem as an MDP. Here the action of each step is defined as the parameterized trajectory. We set the estimated calibration parameters and information gain matches at each step in one vector, named calibration info. In this way, the state of the MDP is defined as the combination of sequence of actions and calibration info at all previous steps, as well as the calibration info at the current step. Finally, the design with wall includes path length, distance from calibration ground truth, reprojection error, information matrix, and empirical rewards such as image coverage and entropy of motions. Our proposed learning framework consists of 4 modules. In the interaction module, the agent interacts with the environment. This is a sequential process of executing trajectory subsequences step by step, doing calibration based on the gathered measurements, and obtaining with wall feedback at each step. The MPC module selects the action of each step in the interaction process using an MPC controller. First, we solve an open-loop planning problem using particle swarm optimization to get the optimal future action sequence. Then only the first action is selected for execution. The interaction data is recorded in a replay buffer to train the neural networks that model the dynamic and reward functions of the environment. The updated dynamic and reward network are again utilized by the MPC controller in the interaction process to generate new data. The first step of MPC is to plan the trajectory from the current step to the last step, maximizing the total future rewards. In this optimization problem, the variables to optimize are future actions from the current time step to the end. The objective function is the total future reward predicted using current learned dynamic and reward models. To solve the problem, here we apply particle swarm optimization, where each particle position represents a potential solution for future actions. We evaluate our method by performing experiments in a simulation platform based on Gazebo. Using this platform, we train the agents to learn different trajectories for camera intrinsic calibration and camera IMU extrinsic calibration. During training, both the intrinsic and extrinsic parameters are resampled from Gaussian distributions after each episode to ensure good generalization. To evaluate our method, we compare our learned trajectories with random trajectories and handcrafted trajectories, which is designed empirically to excite all axes of motion within a certain range. We first train the agent to calibrate camera intrinsics. Here are the learned trajectories after training for 900 episodes. The empirical reward in this case is the coverage of the image wheel with the target observations. Assuming the intrinsics are known, we then train the agent for camera IMU extrinsic calibration. This is the learned trajectory for extrinsic calibration. Here the agent is trained for 1000 episodes with path length and empirical rewards, which is the entropy of motion in all axes. After that, we also fine-tune it with additional information gain and accuracy rewards for 650 episodes. For camera intrinsic and camera IMU extrinsic calibration, the trajectory generated by our learn policy can achieve higher calibration accuracies compared with the random and handcrafted trajectories. The fine-tuned trajectories for extrinsic calibration perform the best as they achieve the lowest mean error and the shortest path length. For real systems when the ground truth of calibration parameters are not available, we could instead use reprojection error for training. Our experiment results shows that favorable trajectories could also be learned in this case. In conclusion, we propose a model-based heuristic reinforcement learning algorithm to learn trajectories that will generate better calibration results for VI sensors. In the future, we will try to combine model-free algorithms to improve performance. Thank you for your attention.